Hello everyone and welcome back to this 8th video dedicated to the FCC reaction section. In the first 7 parts we described the different sections of the process, the characteristics of the feedstock and the catalyst as well as the chemical reactions. Then we saw the operation of the regenerator and we realized the global heat balance on this regenerator. Before going into the details of the future of the regenerated catalyst, it is appropriate to speak about the flue gases. But by the way, these flue gases, what are they made of? And what about the flow rate? We saw that we needed 112 tons per hour of air to burn 7.5 tons per hour of coke. So this flue gases flow is about 112 plus 7.5 equals 119 tons per hour. But what is the composition of these flue gases? First, the carbon of the coke reacts to form CO2. The typical ratio is about 3.5 tons of CO2 per ton of coke. So, for 7.5 tons per hour of coke, we will produce about 25 tons per hour of CO2. It is to be pointed out that the coke formed in the reactor contains a small proportion of hydrogen. This hydrogen amount is variable, but a typical order of magnitude is that about 0.8 tons of water is produced per ton of coke. Thus, the flue gases will contain about 6 tons per hour of water. Note that the coke formed in the reactor also contains sulfur. Indeed, about 5% of the sulfur in the feed is to be found in the coke. This sulfur burns in the regenerator and inevitably turns into SO2. Ultimately, the total amount of SO2 that will be found in the flue gases results from the sulfur in the coke and the amount of desox catalyst in the equilibrium catalyst pool. The desox catalyst is usually made of magnesium oxide. The principle is: this catalyst reacts with the SO2 formed in the regenerator to capture it. The complex formed with the SO2 transforms into H2S when this desox catalyst is routed to the reactor and then to the stripper. Thus, a part of the SO2 produced in the regenerator is transformed into H2S and is routed to the fractionation section. Then, in these flue gases, we can find the nitrogen that has been introduced with the combustion air. This nitrogen flow is about 86 tons per hour, taking into account the fact that air is composed of about 80 volume% of nitrogen. To summarize, these 119 tons per hour flue gases at 750 degrees C are mainly composed of nitrogen for about 75 volume%, CO2 for about 15 volume%, and water for about 8%. The rest is divided between residual oxygen and SO2. So, what to do with these flue gases? These very hot flue gases will be processed in an additional cyclone to remove the last small catalyst particles. Then, these very hot flue gases are generally expanded in a turbo expander to recover the energy of these flue gases. In general, the electrical energy recovered by the expansion of these flue gases drives the combustion air blower. The energy recovered when expanding the flue gases from 750 to 500 degrees C is about 7.7 gigacalories per hour, which corresponds to an electrical power of about 9 megawatts. At the outlet of the turbo expander, the flue gases are still very hot. Generally speaking, we take advantage of this important temperature to produce steam in a medium pressure steam generator. If the flue gases are cooled down from 500 degrees C to 350 degrees C, an energy amount of 6 gigacalories per hour can be recovered. This corresponds to a quantity of steam produced of about 10 tons per hour. Then, generally speaking, we have a final treatment on these flue gases to remove the last catalyst dust to meet the environmental standards requirements. Now that we have described the flue gas treatment, it is time to go back to the future of the regenerated catalyst. See you in the 9th video dedicated to the FCC reaction section. Well, that's it for this video. Thank you very much for your attention and see you very soon for the 9th part. In the meantime, do not hesitate to test your knowledge by answering the quiz and subscribe to my YouTube channel. Refining is exciting. Bye bye!